Okay, so in the previous lecture, I talked about thermal equilibrium, how to achieve thermal equilibrium, how to achieve mechanical equilibrium, and how do you remove the internal constraints that are basically through the wall, and how do you basically arrive at different types of equilibrium. What types of equilibrium are there? You have thermal equilibrium for a simple system we are talking about. So you have thermal equilibrium, you have mechanical equilibrium, and also chemical equilibrium. So these are the equilibria that we have considered. Now as you can see here, you can extend it to, so for example, we talked about two subsystems, right? Two subsystems and the boundary, this is the wall. Here this is one wall and this is another wall. Now you have now three subsystems, and for example you have two components. So let us assume a system. So I just want to show you that the approach that we used, where we made ds equal to 0 and we told the total energy of the system, the system is isolated. So basically the system is, the overall composite system is isolated. Overall the composite system is isolated, but that means it cannot exchange any matter or energy with the surroundings, and it contains three subsystems here: alpha, beta and gamma, right? Alpha subsystem, beta subsystem and gamma subsystem. And U alpha is the internal energy of the alpha subsystem, U beta is that of the beta subsystem, and U gamma is that of the gamma subsystem. And you also have the volumes. So this is the volume, this is capital V volume, V alpha, V beta and V gamma, right? These are the volumes of the three subsystems. Again, U and V, these are all extensive variables, and this is, now we have two components. We have two components, A and B. Two components A and B. So I have Na alpha, that is the mole number of component A in alpha subsystem, and Nb alpha, it is number of, so Nb alpha is basically number of mole number of B in alpha subsystem. Similarly, Na beta represents the mole number of A in beta, and Nb beta is mole number of B in beta. Similarly, you have Na gamma, which is mole number of A in gamma, and Nb gamma, which is mole number of B in gamma subsystem. Now, what are the constraints? So this is something that we have to talk about. Now, first thing, the wall. So the equilibrium is achieved over, means over which the total the entropy of the system has to be maximized, right? ds. So entropy has to be maximized, and we also talked about that extremization of entropy, of total entropy, basically boils down to ds equal to 0, where S is the total entropy of the system, right? Another thing we talked about, and this maximization when we have removed all internal constraints that are imposed to the walls. So for example, the initial internal constraints were like, so the walls were rigid. This wall is a rigid wall, and it is impermeable to A and B, exchange of A and B. So basically the subsystems cannot exchange A and B. So impermeable, rigid and adiabatic. That means no energy exchange between alpha and beta or beta and gamma. Now I remove all these internal constraints. So basically the walls have become now diathermal, permeable to the exchange of A and B. That means A and B can basically diffuse through these walls, right? Across alpha, beta and gamma. And also the walls are flexible. That means they are movable. So you can basically, you are allowing the change in volume of alpha phase, change in volume of beta phase, and change in volume of gamma phase. But what are the constraints? The constraints are the total mole number of A is constant, right? That cannot change, right? You cannot basically create A or destroy A, but total mole number is constant. So this means Na, which is equals to Na alpha, that is the mole number of A in alpha, mole number of A in beta, and mole number of A in gamma. Now you sum it up, you get Na, and this Na is fixed. Similarly, Nb, which is Nb alpha, Nb beta, and Nb gamma, the sum of these, this is also fixed. So Na is, and also the total mole number. So basically, total mole number N is Na plus Nb, that is also basically fixed. So total mole number of A and B are fixed. Na, the amount of Na is also fixed, and Nb is also fixed. And total volume, which is V alpha plus V beta plus V gamma. See, for example, the wall can displace, say wall can displace this way and the wall can displace this way. The volumes can readjust, like V alpha can increase, V beta can decrease, V gamma can increase, or V beta can increase, V gamma can decrease. However, the total volume of the isolated composite system remains constant, like V equals to V alpha plus V beta plus V gamma, which is constant. Similarly, the total energy, see, the total energy, which is U alpha, the internal energy of alpha subsystem, beta is internal energy of beta subsystem, and gamma, internal energy of gamma subsystem. The sum total of that, like U alpha plus U beta plus U gamma equal to U, which is a constant. And as you know, that S is a thermodynamic variable, and it's an extensive function of these three extensive parameters U, V, and N, right? S itself is an extensive function or additive function, and it is a function of these three. So S itself is a function of three extensive parameters. That's what we are writing. So U, V, and N. And as you can see, total U, total V, and total N in this isolated system is conserved. Now, if we proceed the same way, so we can now write S alpha, which is S alpha. So as you know in postulate 2, that S alpha is for each subsystem, the entropy of the subsystem is a function of the extensive variables in that subsystem. So S alpha is a function of U alpha, V alpha, Na alpha, and Nb alpha. Similarly, you can do it for S beta and S gamma, right? Now, if that is so, now you can basically write the change, that is the exact differential ds alpha is equals to del S del U alpha, du alpha, then del S del V alpha, dV alpha, del S del Na alpha, dNa alpha, and del S del Nb alpha, dNb alpha. So this is for the alpha subsystem. This is for the alpha subsystem. And you see, you have del S del U alpha, del S del V alpha, and del S del Na alpha. These are supposed to be the intensive parameters, or a combination of intensive parameters, right? So, and these are what? Del S del U is basically 1 by T. So this will be del S del U alpha will be then del S del U alpha is nothing but 1 by T alpha. Similarly, del S del V alpha is plus P by, so del S del V alpha equals to P alpha by T alpha. And del S del N, so del S del N A, or I can be A or B. If it is I is A, then B is constant, right? Del S del N I alpha is nothing but minus mu I alpha by T alpha. There is a minus sign here, and I can be, I can be A or B, right? You know this, we know this relation. We have talked about this in the previous class. But what I am telling is, we are trying to prove here that the same, we can derive the same laws if we consider multiple subsystems with multiple components. And this is exactly what I am going to do here. So if I now use total ds, that is the total change in entropy, which we are basically at equilibrium, ds has to be equal to 0, right? The extremum value has to be 0. So ds equal to 0 means ds alpha plus ds beta plus ds gamma, which basically gives you ds, right? that has to be 0. Now if I write this ds alpha, ds beta and ds gamma, and we substitute the m and n values, means basically the coefficients in the exact differential expression. In the exact differential expression, what are the coefficients? We have already seen. For alpha subsystem is 1 by t alpha, for beta it will be 1 by t beta, so like that, and for gamma it will be 1 by t gamma, for when I am associating du alpha, du beta and du gamma. So du alpha 1 by t alpha, du beta it is 1 by t beta, du gamma it is 1 by t gamma. Similarly, you have this expression t alpha by t alpha dv alpha, p beta by t beta dv beta, p gamma by t gamma dv gamma. Now you have minus mu a, so for this for species A, so mu a alpha by t alpha dna alpha, minus mu a beta by t beta dna beta, minus mu a gamma by t gamma dna gamma. Right? Now you do it for B also. Now once you have done this, you now make use of this relation, that u alpha plus u beta plus u gamma, which is u, is constant. Now that means what? That means that you can basically write du beta equals to minus du alpha, because du equal to, since du equal to 0, because u is constant, total u is constant, since du equal to 0, du beta plus du alpha plus du gamma, that is also 0. Or then we can write any of these, we can now substitute. We can tell du beta is minus du alpha minus du gamma, right? Because du, total du is what? Du is equals to du alpha plus du beta plus du gamma. Now du itself is 0, right? So therefore du beta is minus du alpha minus du gamma, right? So if it is clear, now we can see one very interesting thing here. Now we can write this as 1 by t alpha du alpha, we keep it as it is, but what we have done here is for plus 1 by t beta du beta, you have written minus 1 by t beta du alpha plus du gamma, right? It is a minus common, right? This is basically minus 1 is common or minus is common, then what I get? Du alpha plus du gamma, right? That's exactly what we have written here, right? So I don't want to confuse you, so I am just erasing this here. So what we are, and this is all happening because du equal to 0. So we are substituting du beta by minus of du alpha plus du gamma, and then you may have 1 by t gamma du gamma. Similarly, for you do it for, so you are doing it for so if I do it for similarly, so I will just do one thing. I have written this. Similarly, I can do it for V. So it will be plus P alpha by T alpha dV alpha, and total V is constant, so dV equal to 0. So minus P beta by T beta dV alpha plus dV. So we are substituting dV beta by minus of dV alpha plus dV gamma plus P gamma by T gamma dV. And then we have mu's, the mu's also we can do the same thing. So instead of mu A and mu B separately, just writing this as minus mu I, I can be A or B, mu I alpha T alpha by T alpha dNA alpha, and this will come plus, not dNA, this will be dNI alpha, where I can be either A or B. So means basically we sum I over A and B. So we have this sum and as well as this sum, right? So so you have mu I, so you are doing a sum here, I equal to A comma B, and you are putting a bracket here. So this will be mu I alpha by T alpha, but see it is minus, there is a minus here. So let us put the minus inside this bracket, minus mu I alpha by T alpha dNI alpha, and this one will be, so mu b, so you have minus of mu b beta by T beta, so this is minus of mu I or mu I beta by T beta minus of mu I beta by T beta. Here I am substituting dNI beta as minus of dNI alpha minus of dNI gamma, and then we have also mu I gamma by T gamma dNI, right? And this minus I can take as common, and therefore this and this I can take as common, so this becomes plus, this minus and this minus becomes plus, right? Now if you look at individually, if you separate them, you have 1 by T alpha du alpha minus 1 by T beta du alpha, right? So basically if I group them now, what I get is equal to, we get this 1 by T alpha du alpha minus 1 by T beta du beta, sorry, not du beta, this is again 1 by T beta du alpha, and you get minus 1 by T gamma, not gamma, just T beta, 1 by T beta du gamma plus 1 by T gamma du, right? We have eliminated or we have substituted du beta, right? So du alpha, so this and plus dot dot dot, we can write everything in dv alpha minus dv alpha, dv gamma minus dv gamma and dv gamma. So and similarly for the mu, right? Now in that case I can now group them like 1 by T alpha minus 1 by T beta du alpha plus 1 by T gamma minus 1 by T beta du. Similarly we can write P alpha by T alpha minus P beta as minus of P beta by T beta du alpha dv alpha and P gamma by T gamma minus P beta by T beta du. It's not du, this is dv gamma. Then we can write minus, then here there is a summation sign. So first let us do the summation sign. there's a plus sign here missing, so you put a plus sign here, and then there's summation over in. So basically, if I do it separately, that is also fine. So I do it for A as well as for B. So I get minus, so this was minus, right, mu A alpha by T alpha dNA alpha, and then you have mu A beta by T beta, and this will be dNA beta is substituted by dNA alpha and dNA gamma, and you have minus dNA alpha. So now this is minus of or plus of mu beta by T beta minus mu A alpha by T alpha, and this will be dNA alpha, right? And then this will be plus mu beta by T beta minus mu A gamma by T, and this will be dNA, right? You have dNA gamma, right? So this is minus plus, and here please note that here there is a minus, and then we can put a bracket. So this will be, so that's what I am writing. So mu A beta by T beta minus mu A gamma by T gamma dNA gamma. Similarly, plus mu B beta by T beta minus mu B alpha by T alpha. See, it becomes dNA. This will be dNA alpha. So this is also dNA alpha, dNB alpha. Yeah, here it will be dNB alpha plus mu B beta by T beta minus mu B gamma by T gamma dNB. Now, as we know that du alpha, du gamma, dV alpha, dV gamma, dNA alpha, dNA gamma, dN beta, and dNB alpha and dNB gamma, they can be chosen arbitrarily, right? Previously we have shown that, right? We have told that these are basically arbitrary. Now, if these are arbitrary, then if ds, now this is basically equal to what? This is equal to ds. Now ds, if I tell ds equal to 0, the individually each of these coefficients, like 1 by T alpha minus 1 by T beta, has to be equal to 0. 1 by T gamma minus 1 by T beta, because du alpha, du gamma, dV alpha, dV gamma, these are arbitrary, right? Because why? Because u alpha, v alpha, or u gamma, v gamma, these are chosen as independent coefficients, right? So independent variables, right? So basically the changes are also, the d's of these are also going to be arbitrary. So as a result, for ds to be 0, the coefficients, each of these coefficient pairs have to be 0. Now that implies 1 by T alpha minus 1 by T beta equal to 0. Similarly, 1 by T beta minus 1 by T gamma equal to 0. This, as a consequence of this relation and this relation, one can write T alpha equals to T beta equals to T gamma. Similarly, one can write P alpha equals to P beta equals to P gamma. Now, if you see, this is the statement of thermal equilibrium. This is between three subsystems, and this is P alpha equals to P beta equals to P gamma is something you can write. That is basically mechanical. And then you have this chemical equilibrium for each species, right? So this is called chemical. These are all equilibrium conditions. Now you will see here, so if I am looking at this, please try to understand although I am solving this T alpha, T beta, T gamma, P alpha, P beta, P gamma, or mu A alpha equals to mu A beta equals to mu A gamma, mu B alpha equals to mu B beta equals to mu B gamma. If you look at the chemical equilibrium, what we are basically solving for, if these chemical potentials are equal, what is the concentration of A that is in alpha, that is in equilibrium with A with beta, and that is in equilibrium with gamma. So basically, if you see, you have these unknowns. You want to find out XA alpha, XB alpha, XA gamma, XA alpha, XA beta, and XA gamma at equilibrium. Similarly, XB alpha at equilibrium means at equilibrium between these three subsystems, right? At equilibrium between these three subsystems. Similarly, you want to find XB alpha, XB beta, and XB gamma. See, instead of mole number, we are looking at X, right? X is mole fraction, right? But that is exactly, so basically we are trying to find out what is the concentration of A in alpha that is in equilibrium with A in beta, that is in equilibrium with A in gamma. Similarly for B, right? However, there is one interesting point. So if you see that XA alpha plus XB alpha equal to 1. Similarly, XA beta plus XB beta equal to 1, right? Because XA alpha plus XB alpha is nothing but, you see that XA alpha plus XB alpha is nothing but equals to NA alpha plus NB alpha by N alpha. N alpha is the N alpha is the total number of moles of A and B put together in alpha. Similarly, you can have N beta and N gamma. Now, Na alpha by N alpha is basically XA alpha. Na beta by NB alpha by N alpha is basically XB alpha. Now, as you can see, for alpha subsystem, you have two components, and XA plus XB have to be equal to 1, right? You can immediately see, because N alpha is nothing but Na alpha plus NB alpha. So you have same denominator and numerator, which is basically going to be equal to 1, right? So now, if you see these relations, what these relations imply? These relations imply that one of them can be taken as an independent variable, right? Say XA and XB alpha. If I know XB alpha, XA alpha is nothing but 1 minus XB alpha. Similarly, XB beta, similarly XB gamma, right? Now, if you look at this originally, you have how many unknowns? T alpha, T beta, T gamma, P alpha, P beta, P gamma, and then you have, say, some XA alpha, XA beta, XA gamma, or XB alpha, XB beta, XB gamma. Now I can take any one of these. So I have now 1, 2, 3, 4, 5, 6, and we can take any of these 7, 8, 9. So I have 9 variables and I have 8 equations. Now if I have more variables than equations, then basically the number of solutions become infinite, right? So basically you cannot define the equilibrium state because one of the variables is unknown. We can basically specify anything. So I can take one variable unknown, I can take any value of it, and then I will always get a solution, and I have like infinite number of solutions. So basically, if my number of variables is more than the number of equations, then one of the variables I can choose arbitrarily. As a result, the number of solutions become infinite, right? But you do not want to determine such a system because you do not have a way to determine an exact equilibrium values of T alpha, T beta, T gamma, or XB alpha, XB beta, and XB gamma if you basically have more unknowns than equations, right? Now what do? We assume, first thing we can do is that if we assume all phases are condensed, that means the pressure dependence is, or PV work is negligible, right? Pressure dependence is negligible, and we can tell that P alpha, P beta, P gamma have to be the same, and that is equal to, say, some P that is known. So P is already known or specified. So P is basically, say, 101325 pascals or 1 atmosphere pressure. Now you can take one set, right? You can take either these things or these things, right? You can take XA alpha, XA beta and XA gamma to be independent variables, then XB alpha, XB beta and XB gamma are automatically determined. So now if you see, if I remove P alpha, P beta, P gamma, because I am talking about condensed phases, that means P alpha, P beta, P gamma are no longer are all fixed to a value P, right? All fixed to some value P. That P can be atmospheric pressure, it can be 3 times atmospheric pressure, it can be also like 1/3 of atmospheric pressure, or whatever it is. It can be some arbitrary pressure, but all subsystems will have the same pressure, right? And we are basically removing this equation, right? This equation is already implied when I am talking about solids or liquids. Now in that case you have 1, 2, 3, and either XA or XB can be your variable. So you have 1, 2, 3, 4, 5, 6. Now if you see, if I remove this equation, for time being, I have 1, 2, 3, 4, 5, 6 equations. I have exactly 6 equations, I have exactly 6 unknowns. So now number of, if I have that, so variables equal to equations, you will have a unique, so we have, so number of variables equal to number of equations. You have an unique solution, right? So this is something that we have to understand. So please try to understand, in this case, if I basically use another subsystem, say delta, and if I tell that you have now this 2 components A and B, you will see that it becomes insufficient, because in that case number of equations is more than the number of variables. So in such a case solution does not exist. If number of variables is less than the number of equations, then you have more equations than variables, then definitely no solution exists, because you can only choose a combination of equations. Other equations become redundant, but you cannot do that. So which equations to choose? Therefore the matrix that comes in becomes non-invertible, and as a result you cannot so basically since it is not possible to invert that matrix, so therefore there is no solution at all. There is no solution. If number of variables, if number of variables is greater than number of equations, you have infinite solution. It's to the problem. But if number of variables is less than the number of equations, there is no solution. Right? Say for example I write 2x plus 3y equal to 5. Then I write x minus y equal to 4. Then I write x plus 3y equal to 1. Now immediately if you see this, you will tell you have 2 unknowns x and y, but you have 3 equations. Now which equation combination should I use? Right? There is no, means we cannot. So as a result, this matrix becomes non-invertible and no solution exists. Right? So if the number of variables is less than number of equations, then there is no solution. But if number of variables is greater than number of equations, then any of these arbitrarily. I can choose one of the variables and fix their value, and as a result, and I can, since it is arbitrary and I am fixing one of the variables arbitrarily, I can take infinite values for that. So I have infinite solutions. Now when it comes to unique solution, number of variables have to be equal to the number of equations. So this is very, very important, and this is something that will again come back when here I am talking about subsystems. Please check. In a system that contains two components, if I am considering an equilibrium across 4 subsystems, you will check that in such a case you have more equations than unknowns, right? So this is something that I will come back to when we discuss Gibbs phase rule, right? So we will come back to that. Now similarly, one can, so we know that we have written this type of function S equals to S U V N, but we also told that S is continuous function, it's a differentiable function of u, and del S by del u with other things constant v comma ni is greater than. So if I have del S by del u, then it has to be greater than 0. That means it is monotonically varying. So or monotonically check this, say for example del S by del u has to be, so for constant v and ni has to be greater than 0, right? That is the thing. So it's a monotonic function, so you can write monotonic function of, so it's a differential, continuous and monotonically increasing function of u. So as a result, you can invert the relation, right? So basically, if you have S is equal to S U V N, that means entropy is a function of internal energy, extrinsic parameter, volume, extrinsic parameter, n extrinsic parameter, number of moles. Then we can basically write this U equals to, because it is continuous and differentiable as well as monotonic function of U, right? S. So you can invert and you can write U as a function of S, V, and both are possible. So if I do that, if I do U, then the exact differential will look like this: du equals to del U del S, del U del V, del U del Na, and del U del Nb, right? And in this case also, the extremization that we will do will come to du equal to 0, right? We will do du equal to 0. You have again the subsystems, but here what we are telling, please note this, here what we are telling is slightly, means it is not really, means how do you say, it is not intuitively clear immediately, right, this approach, because what we are demanding now in such a case, if I start with du, see what we are demanding is, you have S alpha and S beta for alpha and beta subsystems, right? And we are taking like diathermal, flexible, permeable to A and B, and you have alpha and beta subsystems, and you have S alpha, you have S beta, Na alpha, Na beta, Nb alpha, Nb beta, and V alpha and V beta. Now if I look at the constraints, you have constraints which is like in A, V, right? V alpha plus V. But see, we are not talking about constant energy. What we are talking about, because what we are trying to do is we are trying to do du equal to 0. When we write this exact differential, du equals to del u del s ds plus del u del v dv plus del u del na dna plus del u del nb dnb. What we are fixing here? We are fixing, for example, in del u del v, or in the case of del u del na or del u del nb, we are fixing something called s. We are fixing s. Means total entropy cannot change of this isolated system. So what is the total entropy? S, and which is equals to S alpha plus S beta, and this cannot, basically this total S is basically fixed. So the total S cannot change, right, which is S alpha plus S beta. But the equilibrium can definitely. So basically we are telling total energy constant. It is very intuitive. It is intuitive and we can easily understand it, right? Total energy cannot change, right? It's an isolated system. Whatever be the systems of these different subsystems, the total energy is constant, or total energy cannot change, right? That is something that we can easily understand and realize. However, if I tell the other way, when I do it du, I am talking about the other way, where I am telling S equals to S alpha plus S beta has to be fixed. So basically what we are telling, that for du equal to 0, the constraints are Na alpha plus Na beta equal to Na. So these are called constraints. And these are meaningful constraints, right? Because when I tell that it's an isolated system, the amount of Na that you have put, now it has distributed into Na alpha for alpha subsystem and Na beta for beta subsystem, but total Na cannot change, total V cannot change. Similarly, total B right, that also cannot change. Now, but instead of writing u alpha plus u beta equals to u alpha plus u beta equal to u, and telling that u is constant or u cannot change, instead of that, what I am talking about here, when I write du equal to 0, then it becomes S alpha plus S beta equals to S that cannot is fixed for the isolated system. Right? Now, if you have that, so this does not, basically it does not evoke, come out naturally, right? We generally don't talk about like total entropy is fixed, right? For an isolated system also, in general, we'll tell total energy is fixed, not total entropy. So that is why I am repeatedly emphasizing there that even with the du equal to 0 approach, the same equilibrium will come. Okay, however, the equilibrium will be achieved at constant entropy, right? As you can see here, del u del v is taken at constant entropy. Del u del na in entropy is constant. Del u and del nb entropy is constant, right? And then only this del u del s term is coming, right? So entropy here is fixed. The total entropy of the system is fixed. Is what we are talking about, right? In that case also, so as you can see, S alpha plus S beta equal to S, the total, that is your constraint. And then V alpha plus V beta equals V total, that also cannot change, right? So if you have constant S, you have ds equal to 0, dv equals to 0 for constant V, and then total Na cannot change, so dna equal to 0 and dnb equal to 0. Now, so when I do du equal to 0, I can show that this is like T alpha equal to T beta, P alpha equals to P beta, mu A alpha equals to mu A beta, and mu B alpha equals to mu B beta. So you basically, whether you are doing an extremization of entropy, of ds, means extremization of entropy or extremization of energy, both are equivalent, right? Another very important thing, I have mentioned this already, that see, when I am looking at the coefficients, we are seeing these coefficients are basically, say for example, if I look at the coefficients here, del U del S is nothing but temperature, right? Del U del S is nothing but temperature. Del U del V is nothing but pressure minus P, right? And del U del Na is mu A, and del U del Nb is mu B, right? And what we are telling, that the equilibrium is basically T alpha equal to T beta, P alpha equal to P beta, mu alpha equals to mu A beta, and mu B alpha equals to mu B beta. And these are the, now we have these equations of state, right? We have these equations of state where T itself, so by the way, these are, if you recall, these are homogeneous. T, P and mu are homogeneous zeroth order, this I have explained before, functions. So if they are all homogeneous zeroth order functions, that means T, P and mu. Now, if it is homogeneous zeroth order function, what does it mean? These are intensive variables. These variables do not depend on the extent, although S, V, N are all extensive variables, right? So this is how we can think of this. So for example, if I give this example, say this is from Callan's book, that S, so we have S, which is equal to r square by v0 theta. Now r square, r, v0 and theta are positive constants, okay? These are all positive constants, and then you have S equals to r square by v0 theta whole to the power 1/3 and nvu whole to the power 1/3. Now we know entropy, total entropy is an extensive property. So if it is an extensive property, what we know, that if you have S equals to S u v n, you put S, if you use a multiplier lambda and then write S lambda u lambda v lambda n equals to nothing but lambda S u v. But on the other hand, if I write T S v n, lambda n, this is equals to lambda to the power 0 T S V, right? So this basically remains as, so even if S has been multiplied by lambda, V has been multiplied by lambda, N has been multiplied by lambda, lambda can be like a fraction, lambda can also be like 2, 3, 4, right? So lambda can have any value, but this is lambda to the power 0. So whatever amount or extent I change S, V or N, T remains as T, right? T lambda S lambda V lambda N is the same as T S V N. And this example, what we are talking about is some sort of a relation between S, N, V and U, right? Basically S as a function of U, V, N. So this is one relation where R square by V0 theta are basically positive. These are positive constraints, right? Now we will try to see that whether S remains a first order homogeneous function, so or an extensive function. So how do we check that? We write S equals to SUVN. Now what I am doing is I am changing U to lambda U, V to lambda V and N to lambda N. And if I do that, this relation is already known, right? This is known. Now in this case, S is a function of NVU. Now S is a function of, what is this S? This S is a function of this, where you have extensive parameter N, extensive parameter V, extensive parameter U, same thing right here. Now what I am going to do is I am going to put N equal, from N I go to lambda N. From V, I go to lambda. From U, lambda U. Okay. Now if you do that, but there is a 1/3. Are you seeing that? Yeah. So now lambda and lambda V, lambda U to the power 1/3. Now if I am looking at that, it becomes lambda cube to the power 1/3, which is nothing but lambda to the power 1/3. Lambda cube to the power 1/3 means lambda, and then this is basically going to be NVU, right? So basically lambda times NVU to the power, so I have this UV to the power 1/3, right? So this is a valid function, right? This is a valid function which relates S to N, V and U, right? So this is one example that I have taken from Callan's book exercise. Okay, now if you look at another example, again from Callan's book, that again you have r, theta, which are positive constants, but now it is given as S equals to Nu by V to the power 2/3. Now I use the same property, that S lambda U lambda V lambda N. So I use the same property, S lambda U lambda V lambda N. Now if I do that, I am changing here N by lambda N, U by lambda U, V by lambda V. Now if I do that, you see the lambdas cancel here and it becomes lambda to the power 2/3 r by theta square to the power 1/3 Nu by V to the power 3. Right? So this is really not first order homogeneous function. S no longer remains a first order homogeneous function. It is now a 2/3 order homogeneous function. So right, it's a fractional. So that means in this example or in this equation, S does not seem to be extensive, right? If it means extensive first order homogeneous function, right? It has to be a homogeneous first order function. First order function means lambda to the power 1. However, what we are getting here is lambda to the power 2/3. So therefore, definitely this is not a valid expression. It is not a valid expression, right? So now I will proceed to Euler equation. Right, we will do Euler equation next, right? So now means I am ending here and then I will start with Euler equation.